The year was 2019. A signal arrived. It came from deep space. Specifically, it seemed to originate from Proxima Centauri. This star is our sun's closest stellar companion. Proxima Centauri is a mere 4.24 light-years away. In galactic terms, it's practically next door. This proximity makes it a prime target for study. Breakthrough Listen is a huge project. Its mission is simple, yet profound, to find evidence of civilizations beyond Earth. This project uses powerful radio telescopes. These giant ears listen to the cosmos. They scan millions of stars for tiny whispers, signals that might betray an alien technology. The Parkes Observatory in Australia played a key role. Its telescope, Murayang, is a magnificent instrument with a dish 64 meters wide. This telescope was observing Proxima Centauri. Scientists were studying the star's violent flares. Proxima Centauri is a red dwarf known for powerful outbursts. During these observations, something unexpected happened. A faint, peculiar signal was detected. It appeared in the data, a blip, an anomaly. The team of astronomers was intrigued and cautious. Could this be it, the signal they had all been waiting for? It was dubbed Breakthrough Listen Candidate 1, or BLC-1. The name itself held a spark of hope, a potential sign of extraterrestrial intelligence. The initial data was tantalizing. It had characteristics that made pulses race. The universe had seemingly whispered, and we were listening. The quest had begun. So, what made BLC-1 so special? One key feature was its narrow bandwidth. Natural cosmic radio sources are usually broad. They emit radio waves across many frequencies. BLC-1, however, was different. It was confined to a very narrow range of frequencies. This is a hallmark of artificial technology. Human-made signals, like radio broadcasts, are narrow. Then, there was the drift. The signal wasn't stationary in frequency. It appeared to be changing, slowly drifting upwards. This drift was consistent. A signal from a transmitter on a planet would drift. As the planet rotates or orbits its star, the signal's frequency would shift due to the Doppler effect. BLC-1's drift seemed to suggest just such a scenario. Scientists tried to find a natural explanation. Could it be a known astrophysical phenomenon, perhaps a pulsar or a quasar? But BLC-1 didn't fit the profile. Its characteristics were unusual. They did not match any known natural sources. This lack of an obvious natural cause deepened the mystery. The possibility, however remote, remained open. It could be something truly extraordinary. The signal appeared to be coming directly from Proxima Centauri. This star system is known to host at least one planet, Proxima Centauri b. This planet orbits within the star's habitable zone. A planet in the habitable zone, a strange signal. The pieces seemed to fit. The scientific community was buzzing. The discovery triggered an intense period of analysis. This was serious business. The implications were enormous. A dedicated team of scientists got to work. They re-examined the data meticulously, every blip, every spike. They cross-checked everything. The initial detection had been made by a student, Shane Smith, at Hillsdale College. He found it. Then the experts jumped in. Secrecy was paramount. They needed to be sure. The first step was to rule out instrumental errors. Telescopes are complex machines. They can sometimes produce their own strange signals. The team carefully checked the Parkes telescope systems. They looked at calibration data. They compared observations from different times. Was the signal a persistent feature or a one-off fluke? They analyzed data from other observation periods. Did BLC-1 appear at other times? Was it there when the telescope pointed away from Proxima Centauri? If the signal appeared when looking elsewhere, it wasn't from the star. The team sifted through petabytes of data. It required sophisticated algorithms and immense computing power. This painstaking effort took months. Millions of potential signals are detected. Most are quickly dismissed as noise or known interference. But BLC-1 persisted through many initial filters. It kept looking like the real deal. The scientific method demands rigor. This was a true cosmic detective story. As the investigation deepened, doubts began to emerge. The initial excitement started to wane. Subtle clues pointed away from an alien origin. The team found other signals that looked remarkably similar to BLC-1. They had the same narrow bandwidth. They had a similar drift, but there was a problem. These look-alike signals were not coming from Proxima Centauri. They were detected when the telescope was pointed elsewhere. This was a major red flag, a serious cause for concern. This pointed towards a common culprit, radio frequency interference, or RFI. RFI is the bane of radio astronomers. Our planet is incredibly noisy. We humans generate a cacophony of radio waves. Mobile phones, Wi-Fi, GPS, microwave ovens, even faulty electronics. All these things can produce signals that can be picked up by sensitive radio telescopes. The characteristics of BLC-1 started to align with known patterns of RFI. Specific types of human-made technology can produce these drifting, narrow-band signals. The drift, once so tantalizing, could be explained by something as mundane as an oscillating crystal, a component in everyday electronic devices. The signal's features, once unique, now seemed common for Earth-based interference. The evidence was mounting. The alien hypothesis was weakening. The signal was not from the stars, it was from Earth. A disappointing realization for many. So, what was this earthly culprit? What specific piece of technology fooled us? The investigation eventually identified the likely source. It was probably intermodulation, a phenomenon where signals from two different frequencies mix. They combine to create a new, spurious signal, a ghost signal. This new signal can appear at a frequency where nothing is actually being transmitted. It can mimic the characteristics of a deliberate broadcast. This particular interference likely came from human technology, possibly poorly shielded electronics, or devices operating near the observatory. It's a constant battle for radio observatories. They are often built in remote locations, far from cities, but our world is increasingly saturated with wireless signals. Even a distant, faulty device can cause problems. The BLC-1 signal was incredibly faint. That made it even harder to distinguish from true cosmic signals. It was a perfect mimic. The challenge of filtering out Earth's noise is immense. Imagine trying to hear a pin drop during a rock concert. That's what radio astronomers face daily. Our technological civilization is a beacon of radio waves, most of it unintentional, from an astronomical perspective. Scientists develop sophisticated software to identify and remove RFI, but sometimes a signal slips through, especially one that looks so much like what they are searching for. BLC-1 was a clever imposter. The moment of confirmation was bittersweet. This entire BLC-1 episode was not a failure, far from it. It was an incredibly valuable test, a stress test for our alien hunting systems. It showed that our detection methods could find such signals, even faint, ambiguous ones. It proved the pipeline worked, from initial detection to thorough vetting. This is crucial, because one day, a real signal might arrive, and we need to be ready. We need to be able to recognize it. The BLC-1 investigation has led to improved detection algorithms. Scientists learned a lot about these tricky RFI signals. They can now build better filters. They can teach their software to spot these imposters more effectively. This makes the search more efficient. It reduces the number of false positives. It allows researchers to focus on the most promising candidates. Every false alarm, if studied carefully, strengthens the search. It sharpens our tools. It refines our techniques. We also learn more about RFI mitigation. Understanding the local interference environment is key. This means better shielding for equipment. It means stricter protocols around observatories. The cleaner our data, the better our chances of hearing that faint whisper, that genuine signal from another civilization. So BLC-1 was not alien, but the search for extraterrestrial life goes on. It must go on. Proxima Centauri b remains an intriguing planet. Even if it wasn't the source of BLC-1, there are billions of other stars in our galaxy, billions of other potential homes for life. The universe is vast, unimaginably vast. To think we are alone? It seems almost statistically improbable. The quest is far from over. It has barely begun. New telescopes are coming online, more powerful than ever before. The James Webb Space Telescope is already revolutionizing astronomy. It can study the atmospheres of exoplanets. It can look for biosignatures, chemical hints of life. Radio astronomy also continues to advance. The Square Kilometer Array, when completed, will be a game changer. It will survey the sky with unprecedented sensitivity. The tools are getting better. Our reach is extending further. The universe is ancient. It is immense. The probability of finding life, intelligent or otherwise, is unknown. But it is not zero. We have to keep looking. We have to keep listening. The quest continues.